When it rains, water runs over all kinds of surfaces on its way to the ocean. Along the way, pollution such as oils and sediments are carried into our waterways and can be very harmful to the environment. However, thanks to wetlands, there's a buffer between our actions on land and sensitive aquatic environments. Wetlands are some of the most valuable ecosystems on our planet. They provide aquatic and terrestrial habitats for countless species of wildlife and are critical to reducing the effects of on-land activities by humans, such as farming and construction. But our wetlands are in danger. Trash and other forms of pollution have been found in almost every ecosystem on Earth. To get a true picture of the effects of this pollution, as well as other human activity on ecosystems, scientists study certain organisms called indicator species. In wetlands, certain species are particularly sensitive to pollution, such as amphibians and fish, who due to their aquatic lifestyles need clean water. However, the observation of these small species is quite difficult. So instead, scientists move up the food chain and use predators who feed on these organisms, such as large fish and birds, to understand the health of the ecosystem and the food chain. A large population of top predators, such as great blue herons or ospreys, means that the environment is healthy enough to support a large population of their prey species. However, in wetlands specifically, the observation and counting of these species is rather challenging due to the complex geography of wetlands, with many shallow, narrow waterways that keep researchers from using traditional boats, and any researchers that get out and wade through the waterways can damage the environment and startle wildlife. So to try and make observation easier for researchers and safer for the environment, we researched the application of robots to environmental observation. Earlier experiences with trying to develop aquatic robotics demonstrated the challenges in this field, but laid the foundations for our future success. These early robots were designed to try and collect floating plastic, which proved to be quite difficult. The next robots were designed for observation, serving as a platform for cameras and other sensors to monitor organisms in the environment. This robot could be controlled wirelessly and also run autonomous waypoint missions, where it would follow a course defined by points on a map, stopping along the way to collect data, while at the same time streaming video continuously. Additional autonomous capabilities included the ability to identify and track indicator species using the onboard camera and Raspberry Pi. However, the USV only provided two limited perspectives for observation, just above and below the water's surface. In order to get a better vantage point on targets, we developed a multi-terrain vehicle designed to fly, walk, and swim to provide three unique perspectives. Using the TC Williams Robotics team's CNC router, we were able to accurately cut parts for our robot. Even with its advanced manufacturing capabilities, our early designs struggled to operate, so we continued our design process. Our current designs better integrate the flying aspect of this robot and rely more on real-world testing of the walking components that proved successful.
This is the robot. As you can see, it has multiple parts for different terrains. So these legs right here are so that it can go over rough terrain. These paddles in the middle are for water, and the fans on the front and back are for flying. It's mostly important that we're able to go on these different terrain types because that'll give us more vantage points for research, which will make our data more accurate because the robot will be able to see and identify animals from many different perspectives as opposed to just the one.